Okay. Today is October the 18th. This is Screencast number 4. This week is the method of undetermined coefficients and solving them. So share screen. So for this method, we utilize both the homogeneous and non-homogeneous equations to arrive at a formula using a degree of algebra and some methods that we've learned in previous chapters, specifically chapter 3. So we start out with both the non-homogeneous and homogeneous equations. Now this will be represented in the problem with one equation as opposed to two, but it's our responsibility while using this method to separate them. So you start out by solving the homogeneous equation in the first step. You utilize, again, the strategies from chapter 3, y equals e to the rt, giving you usable roots r and r, and either this will be the same, they'll be complex even, but it'll give you roots to the homogeneous equation. From there, you can determine the first solution, and essentially the reason why this is important is because it essentially equates to 0. From the homogeneous equation stated here, it equals 0. Now, the theorem y minus y1 equaling the homogeneous equation, or y1 minus y2, pardon, works because the homogeneous equation equals 0. So 0 plus a solution still equals the solution, which gives you the non-homogeneous answer. So we utilize the non-homogeneous solution equaling 0 plus the homogeneous. This is combined with two solutions, the complementary and the particular. Complementary being the one that equals 0 for the homogeneous, in particular equaling the yt for the non-homogeneous. These are the formats for those answers. You can detail how y1 minus y2 equals the homogeneous solution, and from there you can arrive at a solid formula for the final particular solution, which is, again, 0, this equating to 0, and this equaling the particular solution. So utilizing, like I said, those methods from 3.1, we can arrive at those roots that give us the homogeneous solution. Now, the particular solution is a little bit different. It requires a level of educated guessing based on whatever is on the right side or whatever the non-homogeneous equals to. And it can be a few different things, at least that we've seen in our practice problems in the textbook and in the notes that we've been given. So utilizing strategies, I think, that I've seen on the notes and then also in the textbook, an exponential formula, e to the rt, you basically guess that it is e to the rt as well, and I'll explain why at e to the rt would be used as well in this case in a little bit. Some other guesses for this would be like a cosine beta t plus a sine beta t, and this would be for any solution equating to a sinusoidal. And we also have something to an nth degree. If we have like a cosine times an exponential, or maybe some sort of exponential t, at plus b. The entire point of this is to find the coefficients without really solving for them. And the method itself is actually somewhat simple. It uses a degree of algebra and it can get a little complex, but you arrive at a certain a value that you can plug back in for the particular solution. So once you've guessed and you've plugged in, you find the derivatives of each of these y's. So you derive once, then twice, or in this case it would be up to twice for the second degree homogeneous and non-homogeneous equations, and you plug it back in. And when you plug it back in, you arrive at a form similar to this, equating to some coefficient value times a e to the rt. Now this will have a b in it, or more coefficients based on the degree of complexity, or however many extra variables are represented on the right side of the equation, or whatever the equation equates to. But you arrive at a similar format to this. And using algebra, you can actually essentially cancel out the e's to the RT, and you arrive just with a numerical value and the A coefficient. And through some just very simple algebra, arrive at an A equals the number. This allows you to plug it back in to the particular solution here. And you arrive essentially at an answer for both of them, the particular and the given, and the complementary. Plugging everything all together gives you a general solution to the question. And again, this is just essentially this part equates to 0, and this part is the particular solution. And due to the theorem I stated at the beginning, y1 minus y2, everything ends up working.